টক দেওয়া ছিল হচ্ছে একজন স্পিক করবেন না সব না আমি বলবো না আমি পরের সেশনে চলে যাচ্ছি হ্যাঁ তিনটে হবে Okay, let's begin this session. Our first speaker for today is Bishwarup Mukhopadhyay, who will be talking on the Higgs boson, the particle which stands out in fundamental physics. And with further ado, here he is. Thank you.
I just wanted to make sure that I'm speaking into the mic properly and I'm properly audible. Am I? Thank you. Okay. Let me start by paying my tributes to Professor Bose and by thanking the organizers for, in particular, Professor Kamrul Hassan for inviting me to this great occasion. Okay, let me get into the subject matter in a somewhat matter-of-fact manner and mention that bosons are quantum particles which are of integral spin, something that everybody knows and everybody has heard multiple times this time. Among them, in the world of elementary constituents of this universe, there is just one boson known so far, which is elementary and has zero spin, that is a scalar particle in the Lorentzian sense. This is popularly known as the Higgs boson. It has an extremely crucial role to play in the fundamental theory of weak and electromagnetic interactions, and it also leads to several open issues, raising speculations and intense discussions about possible physics beyond the existing theory, which is called the Standard Model. My story will be based largely on this. However, I will keep the talk mostly at a qualitative level. However, in order to somehow remind people that there is some substance in the matter, I'll occasionally flash a few slides which are technical in nature, which people may take as commercial breaks. Now, this is pretty clear. At the lowest level of smallness known so far, or probed so far, we know the existence of these elementary particles, which have spin half particles like quarks and leptons, force carriers, the photon, the gluon for strong force, and the Z and the W for the weak force, and a spinless particle. Out of these, other than the three force carriers, and of course gluon, which I have kept out because I am talking about weak and electromagnetic interactions, all of them, these part, and the Higgs boson, all other particles or fields as they are called technically in the matter sector are fermions. Now, the first commercial break, which is technical, I'll give a more elucidated version in the slides to follow. There is a standard model of weak and electromagnetic interactions, which is based on a symmetry principle. I'll elaborate on this. And the group, symmetry group, is SU2 cross E1, a product of two continuous groups. And this symmetry, a local symmetry or a gauge symmetry as it is called, implies the existence of four spin 1 force carriers, which are prima facie massless. However, the weak force is known to be a short-range force, which means that it will have to be mediated by massive particles, namely the W plus and minus and C. These three have to be massive in character, which means the symmetry underlying the theory have to be broken without destroying the good properties that the theory has. And this leads one to a mechanism called spontaneous symmetry breaking, which have been also used quite extensively in the context of condensed matter physics, particularly superconductivity. And as a result of this spontaneous symmetry breaking mechanism, a paradigm is sort of blended this way. The unbroken part of the symmetry reduces to the electromagnetic symmetry, which we all know is mediated by photons. Now, spontaneous symmetry breaking is triggered here by the vacuum expectation value, which is the analog of the vacuum expectation value of a simple harmonic oscillator in quantum mechanics. And this value is possessed by a spin zero complex spinless doublet called chargeless doublet. This is a spin zero neutral doublet called phi. And this symmetry breaking process leads, or rather takes us to a mechanism which ends up in a massive W plus W minus and Z bosons along with a spinless neutral particle, which is branded the Higgs boson. Now, this might sound a little too esoteric, so let me speak in simple language about all this and try to establish why the Higgs boson entered as a game changer in the arena of elementary particle physics. The standard model is based on a symmetry principle called the gauge principle, which actually means that the action describing the quantum field theory is invariant under a set of mathematical transformations. This symmetry was originally in a more simple form used in quantum electrodynamics and was found that the theory owes most of its positive features to it. And therefore, when a theory of weak interaction was in the making in the early 1960s, this was a very desired option, and people tried out a gauge symmetry for weak interactions. Actually, technically, it is called gauge principle, but let me loosely use the word symmetry. But there was one additional problem to reconcile with, namely, weak interaction is parity violating. Electrons emerging from beta decay are always found to be spinning in the sense of a left-handed cos2 and never in the sense of a right-handed cos2. So this is called parity violation. Now, if you want to reconcile parity violation and observed fact in nature to gauge invariance, the symmetry principle we are aspiring to have, then an unavoidable conclusion is that all particles must be absolutely massless. Now, this comes as a shock because we know, starting from the electron to heavy quarks, all of them are massive. So, reaching at this unacceptable conclusion kind of get us caught between the devil and the deep sea. A proposed solution came through the spontaneous symmetry breaking paradigm and a mechanism called Higgs mechanism, where actually at least half a dozen people were involved whose name have been displayed several times. There, the postulate is that actually all particles are massless to start with at the quantum field theory level, excepting a new spinless uncharged particle, which is a physical particle, which leaves some energy all over the vacuum. That is quite possible in a quantum field theory, as anybody who has studied one-dimensional simple harmonic oscillators in quantum mechanics must know. Now, if the vacuum is full of Higgs remnants, this is not literal. In a metaphorical way, all particles pushing through the vacuum full of Higgs remnant, they acquire or face an extra inertia and look massive. The exception is the photon, because the photon does not couple to uncharged particles. It is not deterred by the Higgs remnants obstructing its motion. So, and the higher is the mass of a particle in nature, the matter sector that I showed, the interaction of the Higgs boson is stronger. This is also obviated by the fact that when we are walking in a room which is empty, we have certain speed. When we are walking through knee-deep water, we are slowed down, develop an inertia. If it is knee-deep honey, the inertia is even stronger. The surprise is that this is a rather unusual way of conceiving not only a mechanism, but also predicting the existence of an actual elementary constituent of nature, a physical particle, in spite of its apparent exoticity, such a particle was actually observed in 2012, about nearly 50 years after its proposal, and the mass was precisely determined. But there comes the puzzle. An observation that continues to puzzle or stimulate or tantalize physicists is that the very existence of the Higgs boson in a way suggests physics beyond the standard model. Some insufficiency of the standard model is brought forth or brought to the forefront by the very existence and observance of the Higgs boson. There are other ways of inadequacy observed. One of them is most obvious, namely the model of weak electromagnetic and strong interactions has some 20 or more free parameters, which is a rather unsatisfactory feature of a fundamental theory. But let me point to a couple of other difficulties connected with the Higgs boson. One of them called the vacuum stability problem. For example, if we consider a tiny ball oscillating about the inner surface of a hemispherical frictionless ball, the ground state is constituted the bottom of the hemispherical ball, and it is about the ground state or lowest energy state that the motion is studied, and we have a well-laid dynamics for the ball. However, if the bottom appears to a situation where you have a bottomless nadir, then the ground state recedes ad infinitum, and it's very difficult to have a predictable dynamics for the ball. Similarly, in quantum mechanics, if a one-dimensional simple harmonic oscillator had its ground state energy not at h cross omega over 2, but at minus infinity, it would be very difficult to delineate the quantum properties of the oscillator by building over a ground state through the creation operators and so on and so forth. Similarly, the Higgs can reach a no minimum potential energy state, and therefore the whole theory may collapse and fail to produce results or other quantities predicted in terms of the vacuum expectation value of the Higgs. For example, the W boson mass and the Higgs Z boson mass, both of which are proportional to this vacuum expectation value. If this vacuum expectation value becomes minus infinity, the whole theory is meaningless. This is, I mean, with several other complications of refined or rather further embellishments I have left out of my discussion, but this problem is a problem to reckon with. Just one more commercial break. The Higgs boson that we are talking about is a part of a complex doublet of SU2 comprising charged and neutral components. The potential is roughly given by this, as a result of which the potential plotted against the component Higgs fields is of a kind of Mexican hat shape, because the quartic term is positive and the quadratic term is negative in the original postulate. For a large phi, after coming down to the minimum, it goes up. However, the theory is also subject to quantum corrections as you go into higher and higher energy, thanks to what are called renormalization group effects. And that makes the quartic term coefficient amenable to revision, and such revisions may make it negative under certain circumstances. As a result, at some energy, which means for some value of phi, which is a dimension of energy, this turns downwards and again goes to a bottomless nadir, as a result of which we are caught in a rather tight spot. So this is a problem which was noticed early, but was also kind of reiterated when the Higgs was actually noticed, experimentally found that a mass of this and all things agreeing with the prediction of its vacuum expectation value as in the original theory was meeting a somewhat unacceptable consequence. And the unacceptable consequence, in order to make it acceptable, one is reminded that this kind of things becoming negative, some coefficient which is positive becoming negative, is corresponding to a case where there is no additional particle in addition to the standard model particles. If there are, it is possible to reach situations where at some energy it will not be negative. In other words, at some energy where the theory collapses to bottomless situations, there before that level sets in, some new physics takes over and avoids this unacceptable condition. As an example, I am shameless enough to refer to some works of our group around 2050, 40, 15, and so on. It is a matter of constant speculation whether the particle we have seen is the Higgs or a Higgs. That is to say, are there replica, like for the quarks and so on, of the same kind of Higgs multiplets in addition to the basic ones that have been observed so far. Our observation was that if there are additional Higgs-like particles, without leaving out all the technical things, even the simplest extension with an additional doublet with the masses within a TeV can lead to a stable vacuum all the way to 10 to the 19 GeV, which is a Planck scale with quantum gravity scale, not at all known. And overall consistency of the theory, one of which is unitarity. Saving vacuum stability, we are often caught in the quagmire of unitarity, and the amplitudes of Higgs mediated scattering becomes non-unitary. S matrix is non-unitary, let me put it this way. And that in order to avoid that, one has to have the additional scalar particles that occur in the theory closely spaced in mass. Otherwise, also you have some well-known precision electroweak measurements relating the WZ and weak mixing angle value. They are violated. So the two things are solved in one stroke if they are closely spaced in nature. And the observation is that it is possible to have this kind of a possibility tested at the LHC over a large region of the parameter space when the LHC has run for a few more years. With this, I move to a completely different problem, naturalness problem, semi-philosophical, but I don't elaborate why semi-philosophical. The bottom line is that just like an electron moving in a semiconductor develops an effective mass through interaction with the material of the semiconductor, a Higgs mass, through its allowability to interact with other particles in the spectrum, develops an effective mass which is terribly large, making the Higgs mass off by its measured value, from its measured value by some 20 or 30 orders of magnitudes. In order to avoid such a calamity, one has to fine-tune all parameters of the theory at every order of perturbation by 20, 30 places, which is certainly a very ugly situation and technically called an unnatural situation. Now, again, one semi-commercial break. The Higgs mass is not protected from higher order corrections. Any particle means it is subject to a quantum field theory, which is a perturbation theory in the present concept, and it has higher and higher order corrections. These cause the problem for the Higgs mass. This problem is not there for example, electron or a spin half particle, because there is a symmetry called chiral symmetry, which technically controls such large radiative corrections. However, Higgs is being a boson against a la Professor S.N. Bose, is not protected by, doesn't have its mass protected by any symmetry, and therefore the radiative correction in the theory turns out, for the Higgs mass, turns out to be proportional to the energy scale, which is the upper limit of validity of the standard model. If the upper limit of validity is postulated to be 10 to the power 19 GeV or so, Planck scale, then we have a disaster. Naturalness. So, one thing people have proposed or thought about seriously is that the upper limit of validity for the standard model is within a TeV, in which case the corrections are under control. And also one has to ensure that this TeV order upper limit, that is not further destabilized by other quantum effects or radiative effects. This is first lays the legitimate expectation that some fundamental physics is lying within the reach of the LHC. And secondly, the second qualification, namely the TeV scale upper limit, cutoff of the theory, new physics come in, and the new physics whose scale is not further destabilized, is excellently achieved by a theory called supersymmetry or boson fermion symmetry, which can naturally, what by natural means I'm not going into, because there are quadratic corrections which are corrected. That is the naturalness problem, which naturally cancel the large mass corrections for the Higgs. So supersymmetry in a way could come as a messiah to the naturalness problem. However, the problem is that the LHC experiments so far have failed to elicit any signature of the Higgs within mass regions which are safe from the naturalness point of view. There are ways of getting around it and arguing and further arguing. I am not going into that. Instead, I am again addressing another problem which tells us about, I'll have just 3 slides on this and end there. Another problem which is a problem of the heaven and the earth called dark matter problem. This is one reason also why we think that the present standard model of elementary particles is inadequate. It is seen in many ways, I'll come to them later, over the centuries, over the decades, not centuries. This was first observed around, this was first kind of noted, this problem, around 1930s, early 1930s, that of the energy density pertaining to the universe, the amount of energy contribution coming from visible particles, read standard model particles, that is 1/5 or 1/6 the energy density that might arise from actual material constituents. So the 5 to 6 times observed, the observed mass contribution to the universe must come from what is invisible matter or missing mass, or technically or popularly known as dark matter. So there must be some material objects constituting the universe whose constituent cannot be any standard model particle. This has been suggested by first the rotation curves, rotation rates of different galaxies observed by astronomers over the decades, the cosmic microwave background radiation data analysis, lensing effect of gravitational due to gravitational pulls of certain stellar objects, as a result of which light bends while coming around it, all pointing to material particles constituting dark matter. Not all the suggestions are conclusively pointing towards that, but that's a different story. Bottom line is that particles constituting dark matter cannot have either electromagnetic interactions or strong interactions. Why? Because had it been electrically charged for this, then it would have constituted or formed some super heavy atoms in some corner of the space, and the immaculate job done by spectroscopists and astronomers tell us that there is no such evidence. Similarly, strongly interacting dark matter particles might have constituted super heavy nuclei whose excitation and de-excitation would give rise to interesting spectra of gamma rays, which is again obstinate. So if it has to have interaction at all with the standard model particles, it can at best be weak interaction. I emphasize that rest is wishful thinking, assuming that it is weak interaction which they participate in, but this does not have to be the case. However, if so, then one has to look for experimental evidence of the existence of dark matter, and a lot of effort is going in that direction. If it interacts weakly, otherwise it's increasingly difficult, sometimes impossible, to have such signature. What can mediate the interactions? In the weak sector, it is W boson, Z boson, or Higgs. Now, before that, let's have a quick schematic picture. This is the last but one slide. Quick schematic picture. Dark matter can be directly detected if some detector material, say a proton, is hit by it in a experiment, of which there are many going on across the globe, and undergoes elastic collision, as a result of which the detected materials recoil. If it has to be seen in colliders like the LHC, then say the two protons annihilate, and along with some other particles maybe, dark matters are produced, leading to missing energy as signature. And there can be indirect detection whereby they can annihilate in outer space and lead to electrons, protons, photons, etc. But if we concentrate on direct search results on which concrete data exist already in terms of limits, W and Z mediated processes will have unacceptably high rates. What about the Higgs? Unfortunately, no, because one of the latest experiments, for example, called Xenon-1 experiment, very strongly disfavors this, because even with Higgs mediation, it leads scattering rates of this kind mediated by the Higgs, which are too large to be consistent with the presently observed limit. Similarly, there is another problem. The dark matter pair annihilation rate, on the other hand, if it is, this kind of thing, dark matter pair annihilate into standard model particles, that rate also leads to too small a contribution if it is mediated by the Higgs. So again, it is a tug of war, because if the rate is that small, then there is further accumulation of dark matter to make it in conflict with the observed content. There, again, some of us accidentally or non-accidentally, after some banging our heads against the wall, came up with one possibility that if there is a replication of standard model like Higgs, then both of these problems are consistently solved. And what happens is that then there are more than one Higgs-like particles mediating the interaction between dark matter and visible matter. In the case, over a substantial region of the parameter space, the scattering amplitudes for direct search amplitude, there are destructive interference, lowering the amplitude. And when it comes to annihilation of dark matter, there can be constructive interference between diagrams mediated by the more than additional scalars. And as a result, the tension can melt if there is a replication or more extended scalar sector than what meets our eyes. Of course, there are other further implications and ramifications which I have no intention to go on because my time comes to an end. All I can say is that we keep noticing that the Higgs boson and the mechanism it associates itself with represents a very profound truth of nature, corroborated by the actual observation of the particle. But at the same time, it opens the gateway for us to look out and think for additional profound truths lying beyond what meets the eye at the present. So I end with a statement ascribed to Niels Bohr, namely, the opposite of a profound truth may be another profound truth. Thank you very much.
Thank you, Vishwarup, for a very excellent talk, and I'm quite amazed that you have managed to use your time very, very economically. And no, you actually have to have a talk like this. After your name is Vishwarup, so you have to say how the universe looks like. So, indeed. So I welcome questions from the floor, if any. Yeah, over the back.
Please.
Can you hear me? So my question is probably not explicitly related to the topic of your talk, but it's actually about Higgs boson.
Yes.
So I heard there are some, some physicists are working whether there are any varieties of Higgs boson or not. I was watching a documentary some years ago, which in which I saw the physicists are working that there might be other kinds of Higgs boson present in the nature. I mean, what is your opinion on that, and what do you think about the current situation? I mean, the updates of this topic. Actually.
But that is what I specifically concentrated on in the context of two of the problems related to the Higgs boson, namely its vacuum stability, and secondly, its possible role in explaining dark matter related observations. In both cases, some people, including ourselves, have been led to the conclusion that extended sectors of more additional Higgs-like particles solve the problems. This is the tip of the iceberg because, for example, I mentioned a symmetry called supersymmetry, which is a little bit at disrepute currently, but still nevertheless a very strong contender for new physics and general considerations, including that it offers us dark matter candidates. In supersymmetry, for example, the minimal version of the theory must have at least two Higgs doublets and therefore a bunch of other additional particles. So it is not something that is outside anybody's horizon. It is very much considered. And also, if you think very, very naively, there are three families of quarks, three families of electron-like particles, and so on. It's a bit philosophically puzzling to think that the scalars have occurred as a unitary single object. So this is basically my opinion. There is no concrete evidence here, but theoretical or circumstantial evidences that the Higgs, or circumstantial hint that the Higgs sector may be richer than we think.
Yes, sir.
Yeah. You quite rightly said that the quartic potential turns over or could turn over because of the renormalization effects, because of the renormalization group equation telling you that that'll happen.
Yep.
Now, the thing is that there's extreme sensitivity to the ultraviolet, and you have to take into account all the you have to go to a very high level of perturbation theory in order to calculate when it will turn over and what the curve will look like. So I don't know where this matter stands, but do we have any bounds now after the new Higgs
Yes.
mass limits have been put as to whether the universe is stable or not?
Yes. It will take me a few stages to answer through. Am I allowed to answer in 2-3 stages? First of all, when we consider the renormalization group equations which are with the standard model particles are subject to, including the Higgs particle, they are quite well behaved because the theory by then is renormalizable. Therefore, the ultraviolet catastrophes are sort of taken care of through the renormalization scheme. But you are also correct in saying that if this kind of an approach leads to a possible disaster in terms of the downturn, then there one has some problem in applying perturbation theory itself. So one of the ways out is provided by lattice calculations in that. And just before that, it is not just one loop calculation can do it. Almost all conclusions are drawn at least at the level of 2 loops, sometimes 3 loops, where there is a semblance of convergence of the result and some kind of faith in the prediction. There is a next stage of answer is that, after all, in spite of that, our problem is that we are facing a situation where the vacuum is unstable, which means there must be some kind of physics if our particle physics has to make any sense beyond that. Then whether the corresponding RG equations, we work with samples, but in general case, will all be consistent enough to yield proper ultraviolet behavior or not is anybody's guess. So people are also approaching this in view of something that has been very popular so now, namely effective field theory, where you have higher dimensional terms written in the series with some cutoff scale suppressing it, and for that cutoff scale being 10 to the power 4 GeV, 8 GeV, etc., one accumulates, collects, and predicts all the consequences and try to see which kind of things are catastrophic from the dark matter point of view and which kinds are not. Of course, we being lazy or intent to play safe, physicists concentrate on such effective couplings. And the last answer is that, well, I was saying something, but I forgot it. Anyway, ठीक है.
May I ask a question?
Sorry. Yeah. Where?
Here, on your right.
Okay, please.
There are people who have worked on like universes with, so people working on alternative universes, and so working on universe without weak interaction. So if there is a universe without weak interaction, then the only dark matter candidates are what they conclude is axions and primordial black holes.
But axions do participate in weak interaction in their way. We have heard a very nice talk on axions yesterday.
Yes.
They do participate in.
But you could have axions even without weak interactions, perhaps.
Okay, maybe, I don't know.
Yeah. But so, but how does your, Higgs model play in that?
Practically nothing, because as I said, even this sets of conjectures about additional Higgs particles or whatever, they are based on this expectation that dark matter cannot interact electromagnetically, cannot interact strongly, but it can in principle interact with standard model particles via weak interaction. But again, there is no guarantee. So there are some colleagues of ours who, without thinking of parallel universes, in our universes are focusing on the situation where the dark matter does not interact anyway excepting gravitationally. Okay. In which case, all its features seen from CMBR, from galactic rotations, etc., are reproduced. But nature, nobody can expect nature to have created this universe with the aim that human beings, through their conventional and restricted processes, should be able to detect it. So dark matter may be completely undetectable in the direct search session, in colliders, or in indirect searches. In that case, the only signal should be gravitational, observed through astrophysical and cosmological processes. There are people who are concentrating on such options, and quite rightly so.
Yes. And in one case you wrote like, if it is not finely tuned, what is the problem with that?
I have to interrupt because partly we are running rather late. I suggest that the discussion be carried out outside this.
Yes, okay. I'll be always there.
Okay. So meanwhile, let me thank the speaker again. And with that, let me welcome our next speaker, Professor Shamaldana, who will be talking about tripping phenomena in nature. Is it tripping or tipping? Tipping. Okay, so it's it's right. So tipping is fine. Tripping is bad because then you get hurt.
হ্যালো, সুপ্রভাত তো বলতে পারছি না, 12টা পার হয়ে গেছে। তা ঢাকায় এলাম, 2-4টে বাংলা শব্দ বলবো না, কি হয় নাকি? তো যাই হোক, কামরুল তো এমন ব্যস্ত রেখেছে গত লাস্ট 3-4 ডে যে ঢাকা দেখার সুযোগ হয়নি। আফটার 12 বছর পরে এলাম, ঢাকার সুযোগ দেখার এখানে হোটেল, এখানে লেকচার রুম, মাঝখানে শুধু কাচ্চি বিরিয়ানির কথা শুনেছিলাম, কাচ্চি বিরিয়ানি খাওয়ার সুযোগ হয়েছে। একদিন হাঁটতে হাঁটতে মেট্রোতে চড়ে এসেছি, আর মামার রিক্সাতে চড়েছি, এইটুকু অভিজ্ঞতা হয়েছে, এখনো ফুচকা খাওয়া হয়নি। যাই হোক, now coming back to this conference and celebration, I thank Kamrul. He has been talking to me about celebrating the 100 years of Bose, the discovery, last 2 years. আমার কানের পোকা মেরে দিয়েছে। তো I'm happy to see that he made it and it is successful. Thank you, Kamrul. So, regarding Bose, actually I first know about Bose when I was a student of class 9. I have a book in organic chemistry book by Shamar Guho in Bengali. And he introduced the book and he wrote about, appreciates that such science books should be written in Bengali. Banglaয় Vigyan Proshar Ottanto Joruri. He wrote these words. So that was my first introduction to Bose, or understanding of Bose. And then when I was master's, then I studied the Bose-Einstein statistics, of course, formally. But I want to share one experience. When I was in Germany, usually I travel to Germany, I have several physicist friends. They call it Bose-Einstein statistics. So I'm sorry, I said, sorry, it is not Bose, it is Bose-Einstein statistics. And he was born in Bengal, doesn't matter India, but he was born in Bengal and he was Bengali. So this is my small contribution to this title and his pronunciation. So I'm very happy to be here and watch Kamrul is really organizing so nicely this conference. Now I'm going back to my talk. As Arshad has said, that it is about tipping. So it is not about Bose-Einstein statistics. So it is about complex systems. So if you look at, so I'm still puzzled, what is the definition of a complex system? I tried to write down few points. I say bullets, you can see that it is high, it should be high dimensional. It is high dimensional system. So, and difficult to model or define mathematically. And mostly they're difficult to predict the future. Besides this point, there should be more and more points. So I think knowledgeable audience could add. I left the bullets for them. However, I'm going to talk about low dimensional system which is also behaves, the behavior is like a complex system. So this is the tipping, the book I read in 2000, Tipping Point, read by Malcolm Gladwell. He said the small things can make a big difference. What is that? So this was a very interesting example. This is a suede shoe. It's called Hush Puppy shoes by American brand shoes. In 1984, the cell, this was usually sold at a small outlet in a small village in US, and the sales goes down to 30,000. The company was thinking about closing down this particular shoe. So what happens one day in the New York, Manhattan birds, few people came up with these shoes. And slowly the companies, some of the, designer companies, fashion designer company started ordering this shoe. And then slowly what happened, some celebrities going to their show with these shoes. By 1 year, the sale shoots up to 430,000. So he defined as a slow effect that creates a huge difference in the cells. So this is also true for the disease spreading. We know the pandemic, it started with a small assumedly in China, then it spread into the whole world. Also the revolution, change of a political regime, it may start with a small perturbation that it can grow, and finally it leads to a regime change from one government to another government. I think Bangladesh has observed it very recent time. This is also a tipping, I would say. So with this, I come to my title, Tipping in Nature. I will focus on ecological system. Rather, I will give it, let me say, before going to that, let me introduce my collaborator. This Oyanava Bosak is a young student, and he did most of the hard works. And then my collaborator, Nanda Boiragi, he was the PI of this project. And our friend Ulrike Fardel, she also assisted in this work quite a bit. Okay, so the outline is okay. I'll introduce briefly what is tipping in nature. So I start with the title, the tipping in nature. And I will try to share my experiences on two aspects, that is tipping in population model with external impulses, and then the partial tipping. I will possibly stop if I cannot finish the whole thing. It's not important. So let me go to the tipping elements, where the tipping is usually observed in nature. First one is Amazon rainforest. Say an optimal temperature I can read out. An optimal temperature allows a maximal growth of vegetation. A negative growth rate implies tree mortality or desertification. So Amazon rainforest dieback is a famous example. It's a tipping element which responds to El Nino. An Indian summer monsoon, if the planetary albedo is the fraction of light reflected from the Earth's surface, exceed for suffering sufficiently long time, the monsoon season disrupted or stopped. So this is Indian monsoon also a tipping element, susceptible to tip. And one of the famous one is Atlantic meridional overturning circulation, or called AMOC. Addition of a fresh water on the Atlantic Sea with warm surface water. If there is a hosting of water, cold water, or from the Greenland, then it could really stop the AMOC circulation. I will come back what is AMOC circulation, explain in the next slide. Now also the ice cap in the Greenland. So I'm giving two examples in this one. If you look at this, so this is more covered with ice, and this has a less ice. So these are the two states. Ice and no ice is the two different states. So this can happen. And if there is a melting, the cold water goes to the Atlantic, and there is a kind of hosting that would create the AMOC, stopping of AMOC. And right side is the blue one is the cold circle under the water, and the reddish one is the warm circle water cycle above the surface. So this AMOC circle continues in the Southeast Asia too. If this stops at certain point of time, what can happen? You can understand how it affects the nature. So there is a prediction that after 150 years, there is a possibility of stopping this AMOC cycle. Anyway, these are all predictions. I said that prediction of such phenomena is always difficult. So for the young students, before I go to this more details, I would introduce a bit about what is nonlinear dynamical systems. On the right side, you can see that this is a type of differential equation where S is the vector. It could be one-dimensional or scalar. It could be one-dimensional, it could be multidimensional. And if you solve this equation 0, then you can get equilibrium points. Then equilibrium points can be steady state or simply equilibrium, or it can also create oscillatory motion if it is more than three dimensions or more dimensions. So systems, we can classify the equilibrium systems and non-equilibrium systems. The AMOC and all these are equilibrium systems. They have coexisting steady states. I will come to that point. And what is a steady state? If we can define this one equilibrium points, and if let us see this is a steady state. If for any initial conditions, all them converge into these, so negative Lyapunov exponent rather, then it is called a steady state or a fixed point. If there is one unstable direction and one stable direction at the fixed point, then it's called saddle point. This is the very basic idea. They can coexist in a system separated by a boundary of initial conditions. And another example is here. This is steady state. This is a stable steady state or node. This is separated by an unstable manifold. And here is a circle, limit cycle. These two coexist. So such situation can appear in a nonlinear dynamical systems. So first of all, I'm giving an example. So let me see what is the basin. So you see that this is a hill and this is a river, two sides. If a rain drops here, this arrow like this is a very unstable state. Rain drop either may go this side or may this side. If it goes this side, then it flows through the river. So this river, all this region, the water collected or rainfall collected, it will go through this. This is the basin of this river. And also this is the basin of this river. It can be explained like this, a double well potential, we know all this, that this is a stable steady state, this is a stable steady state, this is an unstable steady state, and from any initial condition from here, it will converge here. For any initial condition here, it will converge here. And if it is take initial condition here, we do not know whether it will go to this side or this side. So this is the uncertainty. So this is why we call it unstable steady state. So with this few introduction, I come back to this one. The previous equation, I have seen that lambda is time independent. But I'm going to the regime of non-autonomous system where there is a parameter which explicitly depends upon the time t. So here we say, and now what happens in the nature? A parameter can vary linearly with time. A parameter can increase linearly but with the oscillatory motion. And there a parameter can also increase in time with a additional noise in it. So three different possibilities how a parameter increases in time. So this is the basic seed for the tipping we are going to study, which is different from the Gladwell understanding. So by that way, so far, the tipping is also one way called is critical transitions. So there are three types of tipping: are bifurcation tipping, rate-induced tipping, and noise-induced tipping. So I will explain one by one. So let me go back to it again, the bifurcation diagram. If you change a parameter, if you take the initial condition above this line, it will converge here. You will get a solution. Let us take a lambda. For particular lambda, you will get it, and rather the parameter lambda, you will get one initial conditions. If you slowly change it, you can get another steady state. This corresponds to one value of the parameter, this point corresponds to another value of the parameter, and this point is another value of the parameter. So if you change the parameter slowly, the equilibrium state changes. And here we have a S-like bifurcation diagram. This is an upper stable state, and this is lower stable state, and this is an unstable state. So what happens, you look at that, not only the curve of the equilibrium state changes with parameter, also the potential function changes. At this point, the difference from the distance from this unstable state is large. A lower steady state is small. It is expressed by this potential function where this is a shallow and this is a deeper one. So this deeper one corresponds to this one and the shallow one corresponds to this one. And when you change the parameter, you see that the potential function changes because here the distance from this upper steady state from the unstable state is smaller and the lower steady state has a larger. Accordingly, you see that this shallower well and the deeper well. And when it comes to here, there is only one unimodal, there is no double mode. So becomes monostable state, and it falls down to the lower steady state. So these are basically behavior when you slowly change a parameter to draw a bifurcation diagram. And this is also can be explained here, the similar thing, but with a particular model here. So if you try with this model, you can play with the parameter b, keeping it a constant, or keep b constant and change a. If the students can try the simplest model and verify this result, this equation has an upper steady state and an unstable state, and there is no other state here. So if you change the parameter b slowly, if it's a point, I think I do not see, is 2, the potential function changes, this oil becomes shallower and shallower, and finally, if you keep a ball here, it will fall down. So that happens here. This, and then fall here. I mean, the students can try this simple model to verify this one. Now, actually, how the tipping depends upon the rate of the change of the parameter. Here is an example. If you change the parameter with this way, then keep constant, this is a saddle point, this is saddle point, upper steady state and lower unstable state. It slowly, there is a change of state from here at the meeting point or the saddle node point to the drop down to the lower steady state. But if you change at a higher rate, the green one, what will happen? The trajectory also try to come away outside this stable state, but it will return to the steady state. But if you take a little slower than this speed, change the parameter, it will leave the steady state early and come down to the lower steady state before the saddle point. So this is called rate-induced tipping. So it depends upon a critical value of the rate of change of the parameter. I mean, this is a systematic way of recent studies of tipping using simple models. And there is another noise type. This is also, noise is predominant in nature, you know, that here you can say the same diagram, the lower steady state, upper steady state separated by the unstable steady states. But if you add a noise in these simply and increase the parameter, it will tip, it's supposed to tip here at this saddle point, but it tips up to the upper steady state before this saddle point. And here if you go on decreasing this parameter in this direction, you see that again it drops down to the lower steady state before the saddle point. In bifurcation diagram, usually it will drop down here or go up here. But it is happening, the tipping, that system changes from the upper steady state to lower or lower to upper before this saddle point. Why we are studying such S-like bifurcation diagram with two saddle points? Because it exists in nature. I mean, with using simple models like global warming, Indian summer monsoons, people have studied from the data. They tried to model this dynamical system or tipping elements, and they find the similar bifurcation diagram. The upper steady state, lower steady state, different by the unstable steady state. Here also, it is a global warming has a similar phenomena. It's a carbon dioxide and the temperature rise. So upper steady state, lower steady state with this. So such S-type bifurcation diagram is really existing in nature. So this is the people are studying with such models, simple models, to understand the basics or fundamentals of tipping elements. So this is another example. You can see on the left side, figure A, parameter changes here. The parameter increases linearly, and it crosses a value 2. 2 is the global temperature. Global temperature is allowed by the IPCC 2 degree. So we should restrict the temperature rise below 2 degree. We should restrict the carbon dioxide emission to keep the warming below 2 degree. So when it crosses this threshold, what could happen? It could show up to different behavior. Either the system upper steady state from changes to the lower steady state very slowly or very fast. So here is demonstrated further. This is a saddle node bifurcation point. It could really tip immediately at the bifurcation point, or it could be delayed in time. So such two behaviors, different behaviors, slow onset of tipping, this is a fast onset of tipping, it is a slow onset of tipping. These are observed in the models of Amazon forest dieback model or Indian monsoon model. And the slow one is observed in AMOC model and ice cap model. What happens if we do not change the parameter linearly, but if we give a shock like this? There is again a temperature threshold. Shock could be like a going up with a speed and withdrawing with another speed. I mean, withdrawing means going up above the threshold and going down below the threshold. So these rates are identical, and the time duration of time with above the threshold is smaller. What happens if we have a smaller height of impulse, but longer duration and two different speed, increasing and decreasing speeds are different? So two different impulses on the parameter, usually it happens from the external environment. What will happen? For this case, where it is larger strength of the impulse, but small duration, it could still recover. It leaves this upper steady state, but it still could return to the steady state. But even if it's a lower impulse in height, but longer duration, and it could really take a trip. So what is the take-home message about this? Take-home message is a faster rise and fall in global warming exceeding that threshold may not tip a system, even the strength of the warming is larger. On the other hand, a slow but longer duration of time exceeding the threshold impulse can induce a tipping. So again, I repeat, height of an impulse above the threshold is important, but active time interval of an impulse exceeding the threshold is more important. I will show you with my. So now I'm coming. What is the time? 7 minutes. Okay. So now I will come to share my experience. When do multiple impulses, such impulses, due to environmental variation, trigger tipping in ecological system? So this is a single one-dimensional system, which has, this is the growth of this worm. This is greener. So, and this is a external predation, and this is a carrying capacity. It has 3 steady states. I will come to that. So if the population is large, then greenery is gone. So greenery and no greenery are the 2 steady states. It depends on the high population of the worm is the low. This is for the low population of the world. This is the high population of the worm. So this is expressed in a phase diagram. The rate of growth of the population of the worm, and this is the carrying capacity. Then here is a huge refuse state. Refuse state means low population. The system, the greenery can exist. But there is another, this magenta state with a high population, greenery is gone. In between the white area is for the unstable steady state. So if we make the constant the parameter r and move on increasing the k0 slowly, we have a bifurcation diagram like this. The upper steady state and lower steady state separated by these unstable steady states. And the most desirable state is the low population at this stable state. So we took this bifurcation diagram here at this saddle point and started with this upper steady state and want to see when it could tip to the lower lower steady state. So we increase, we rather decrease, we decrease, because if you want to really go to this state, you have to decrease the K0 in this direction. So we linearly decrease this one, and this is the saddle node point, K1. If we decrease on, at this point, the unstable and stable manifold, they meet here. If we start the initial condition from here and here, we find that it doesn't tip here. It's so a slow onset, it's a delayed tipping to the lower steady state. And it doesn't depend on the initial conditions, always tracking the same path. So this is almost known, but we have verified it with our model system. And if you change the rate of the change this, you see that the tipping delay is only changing. I'm not going into detail of this, but this is an important result. Now we have applied an impulse with identical rate and height. Then you find that a trajectory starting from this initial condition followed this upper steady state, then it goes transition to lower steady state. But if the impulse has a narrower, for smaller duration of time, it doesn't tip. It tries to tip, but it goes back. But it is undesirable. For this system, going to the higher population is undesirable. We want a tipping. So we want to push back to the lower steady state, a low population state. And what you do, what you try, we apply this first one, we apply a smaller height, pulse of smaller height, longer duration. And then what happens, it really tips. So why we use this strategy? Because in earthquake, if there is a large earthquake peak, then it was followed by concurrent other peaks. So taking that example, we applied to simultaneous successive impulses with a delay. Of course, there are a lot of other things. I'm not going to that. I think I should stop here with a nice animation. This was really highlighted in the chaos. That these are the two worlds. This ball can coexist either of this or this. For the large impulse, we are expected that this ball should come here, but it's not sufficient enough to push to this one. It goes back to the original upper steady state. But when you apply, after this, when you apply a smaller impulse, it really goes to the desirable lower steady states. So with this, I thank you. I think it is enough. If you want to conclude me, let me say, I've introduced briefly what is tipping and why it is important for area for research. This is the most important message I want to convey to the young students or young researchers. Bifurcation tipping in an ecological model I have tried to describe. Tipping is usually delayed with a rate of change of the parameter in particular example case. If one large pulse fails to induce tipping, a secondary impulse of smaller height can really induce tipping. So with this small conclusion and observation, I stop here for your questions.
We're running actually a little bit behind, actually not just a little bit behind, quite a bit behind. Are there questions? I would like to entertain only 2 questions from the floor. Okay, if...
One.
Sorry, could you please... Oh, sorry, you're just at a critical angle.
Yeah.
You are not at an angle to tip me over.
So is the tipping is a kind of phase transition?
Why not? Critical transitions, yeah. But it could be first order, it could be second order, in a sense, you can say.
Okay, that has no one discussed that, or?
Yeah, and not in the sense, phase transition in the sense. But
Okay.
second order, always a history says no one has studied that too. Yeah. So not more interested in because how long we are still to wait. The amok-like phenomena could stop. They're trying to predict those things. So how the monsoon onset in Indian monsoon onset and offset, they're more interested about studies of these things. Like in our ecological model, we are more interested, okay, how to induce the low population of worm in the system. So something like that. So people are more interested. Although the people, yes, agree that it is also another critical transition. And as I said, that is a fast onset and a slow onset because this represents the first order or second order transitions.
Okay. That was a nice talk. Thank you.
If there are no other questions, I would like to thank the speaker again on behalf of everyone here. And I would like to usher the last speaker for this session, Dr. Nafiz Ishtiaq, who will be talking on Kramers-Wannier duality in the non-abelian Ising models.
Thank you. As a relatively recent graduate of the physics department of Dhaka University, it is a great pleasure and honor to be a part of this conference. And I would like to thank the organizers, especially Kamala Sansar, for giving me this opportunity. So, I will be talking about some two-dimensional classical statistical models. Yeah, so, I will be talking about some two-dimensional classical statistical mechanical models on lattices. They are related to one-dimensional quantum mechanical problems, but I will be using the classical language. What I will be talking about does not have a direct connections to Bose-Einstein statistics, but of course we share some very general motivations. For example, we would like to know how to study the phases of matters and what are the good models for describing different states of matters, whether we want to use a Lagrangian descriptions or an operator algebra descriptions or something else, whether we want in continuum or in lattice, etc. And of course, the role that symmetry plays in understanding the phases of matters was well understood, even well long before the time of Bose, but since then it has only become more and more important. So for example, we would like to know what kind of symmetries our systems have, what are the global symmetries, what are the gate symmetries, and etc. And we would also, of course, like to know whether there are dual descriptions of the same underlying physics. Now, I will describe some recent theoretical tools that were developed to study these kind of problems, and I would like to demonstrate all the things that I will say in one of the simplest models that you can imagine, the two-dimensional Z2 Ising model. Since I will be talking about this model, let me spend some time describing what it is. So this model is defined on a two-dimensional square lattice, but doesn't have to be square. I'm just drawing it as a square for simplicity. So the lattice consists of edges and vertices. And at each vertex, you can have either +1 or -1. And given a configuration like this, you assign a weight to this configuration, a real number, and then you sum over all possible configurations and you sum over the weights. So this is what the Boltzmann weights look like. So E represents an edge. So for example, this is an edge. S is the source of the edge, so this one, and T is the target, so this one. So sigma TE and sigma SE refers to the numbers at the source and the target of your edge. So then you sum over all the edges, you sum up all these numbers. This beta is the inverse temperature. You take the exponent, and then you sum over all possible configurations of numbers that you can put on the vertices. So this gives you the Partition function of the Z2 Ising model. This is a very old model, as you can see. It was studied while in the 20s. Now, this model has a famous duality called Kramers-Wannier duality, which relates a low temperature theory to a high temperature theory. So notice that at low temperature, this model prefers that the numbers at the two endpoints of an edge are aligned. And at high temperature, it prefers that they are opposite. So the high temperature is the disorganized phase, and the low temperature is the organized phase, or the ordered phase. But the Kramers-Wannier duality says that the partition function, so if you consider on a lattice, so I'm calling my lattice sigma, with some inverse temperature beta, then this model is dual to another model with a different temperature. Well, this is some function, and if you don't know what it looks like, if you plot it, so if this is beta, let me call this beta check. So it kind of looks like the inverse function. So if you have one theory at low temperature, then the dual theory will be at high temperature. So this tells you that a high temperature theory and a low temperature theory, even though they look very different, they can be describing the same basic physics, essentially. So if you plot temperature here, so then this duality relates a low and high temperature models. And we know that these two different temperatures are in two different phases. One is ordered and the other is disordered, which means that at some point there's a phase transition between these two phases. And the phase transition must be the self-dual point under this duality. So there's a critical temperature. So you can easily compute the critical temperature by saying that beta is equal to beta check. This gives you the critical temperature. And this, of course, is the correct temperature. Well, so this is a very simple model where we can study phase transition. Now, this is perhaps a bit too simple, and we would like to generalize this model to describe more practical systems. So suppose we have some thin sheets of metal or something like that. Just the Ising model is probably not going to work, but you can try to find generalizations. So some generalizations are easy to do. For example, we can extend the symmetry from Z2 to any abelian group. And the Kramers-Wannier duality acts essentially exactly the same way. And this was shown a long time ago by Wegner. But even just abelian global symmetry is perhaps a bit too simple. Some other things that we would like to do is that we would like to consider non-abelian symmetry. We have heard a lot of talks where there were gauge symmetries. So we would like to be able to couple a matter described by the Ising model to some kind of gauge theory. Right? Because today we heard a talk about standard model, so there are many matters, and there are many gauge bosons mediating forces. So we would like some kind of model for that. And the Ising model has nearest neighbor interaction. Ideally, we would like long-range interaction as well. And of course, we would like to know whether there are dualities between these models. Okay. Now, these things, although they're more practical, they're also harder to do because the way that this theory was developed, people found very clever ways of computing the partition function and then manipulating the partition function. But that gets extremely complicated when you introduce non-abelian symmetry. So we need better tools for doing computations. Now, one idea that was proposed relatively recently is generalized symmetry. So what it means is that, well, so let me go back a bit and talk about the Noether's theorem, which most of us must be familiar with, which says that if you have a symmetry in your theory, then you have a conserved current. So here I'm calling the symmetry a zero-form symmetry, by which I simply mean that these symmetry transformations act on local or zero-dimensional operators. And this theorem tells us that we then have an associated conserved current. So what I'm going to say is that the existence of a conserved current implies that you have codimension 1 topological operator. So what are these things? So suppose you have a current J mu, which is conserved. So you can just define a 1 form using this current. And this is your conservation equation. Well, this is just a notation for the divergence. So now, the point is that this hot star J is a d-1 form if you're in a d-dimensional manifold. So what that means is that if you take any closed d-1 dimensional manifold and integrate star J over it, then this quantity that you're getting is topological because of this conservation. So what this means is that, so this is an operator. So we are familiar with local operators, things like OX, so where X is some point. So these operators are located at a particular point, but this operator is more extended. It is located across this d-1 dimensional subspace. And just the way that you could insert these operators in your correlation functions, you can insert these extended operators in your correlation functions. And topological means is that if you change the support of the operator, if you bend the surface, so to speak, then the correlation functions are not going to change, as long as you do it smoothly. Okay. So a variation of Noether's theorem that has become very useful is that the existence of a p-form symmetry means the existence of p+1 codimensional topological operator. So recall that zero-dimensional symmetry is what acts on local operators. So p-form symmetry is what acts on p-dimensional operators. And the Noether's theorem for this kind of symmetry is that there are p+1 codimensional topological operators. For example, so suppose you have a local operator O, and in 2 dimension, you have a topological line operator G. So G may be a transformation. So now if I move this line across the operator, then this line induces the action of G on a local operator. That's it. So having a symmetry action on your operators, something like G, means that you have these kind of topological lines that you can move across operators. So another perspective on global symmetry is that you can say you have a global symmetry if you can couple your theory to a background gauge field. Okay, so background gauge field means that it tells you that if you move an operator around, how does it change? If you don't have any background gauge field, then the operator is not going to change. But if you have a background gauge field and you move your operator from one point to another point, then this O is going to get transformed by one of your symmetry transformation. Now, if you have discrete symmetries, for example, and I should say, in this talk, I'm mostly going to talk about discrete symmetries, not Lie group symmetries. So if you have discrete symmetry, then how do you implement the idea of a connection or a gauge field? So you mimic this definition, that a background gauge field tells you how to parallel transport operators. So you can do that by putting a network of topological line operators labeled by group elements, so that if you move an operator around, then whenever you cross a line operator, your operator is transformed. So a network of line operators labeled by group elements is the analog of a gauge field when you're talking about discrete symmetries. But these line operators will have to satisfy certain constraints. For example, if you have 2 of them, and if you have a local operator, so if you first move this across O, your operator gets transformed by H. Now if you move this again, it gets transformed by GH. But you could fuse these 2 line operators. So recall that they're topological, you can freely move them around. So you put these 2 together, so that gives you a new operator. So let me call that just G tensor H. So this is just my notation for calling this line operator that I get by fusing 2 labeled by G and H. So I can move this, and my local operator is transformed by G tensor H, right? So, but I could fuse this and get to here as well. So these 2 things must give you the same answer, meaning that this G tensor H must be the same as GH. So fusion of line operators must satisfy the same relations as the group multiplication. So G tensor H must be GH. Another thing is that if you have a junction of topological line operators labeled by different group elements, and if you move a local operator around and come back to itself, so it must come back to itself. Otherwise, this operator becomes ambiguous. But if you just move this around, you see that it picks up a product of all these 2 group elements. So this product must be identity. So the point is that these topological lines representing transformations, symmetry transformations, they must satisfy some constraints. They must fuse in a certain way. And if they meet at a junction, they must meet in a certain way. If you're a bit careful and if you figure out all these constraints, you'll find that the labels of the topological lines form something called the fusion category. The exact definition doesn't really matter. All it means is that these lines, they satisfy certain constraints, very similar to groups or representations. Let me give you some examples of fusion categories. For example, we are all familiar with group-like symmetries. So there is a fusion category that has essentially the same data as a group, and it's called VEG-G. And this has many, many objects, but the elementary objects are really just the elements of the groups. So whenever you see vec G, you should just think of the group G, and nothing more fancy. And then you have rep G, which is the category of finite dimensional representations of your group G, which is something that we're also kind of familiar with, maybe not necessarily in this language. So this is just some object that has many vector spaces inside of it, and all of these vector spaces have an action by the group G. Now, another category, which may seem more esoteric, is called Ising Z2. It has three elements, epsilon, 1, and sigma, and they have certain product rules, which it doesn't directly correspond to something that we are very familiar with, but these three elements label the three topological line operators in the Z2 Ising CFT. The Z2 Ising CFT is one of the simplest universality classes, and one of the simplest CFTs that we can imagine. It only has three primary operators. And these three labels are basically those three primary operators. And in the CFT language, they're called Verlinde lines. So the point of this example is that even though these fusion categories, the definitions seem a bit formal, they're something that we encounter even in the simplest theories that we know. And this is even non-invertible. So it's an example of a non-invertible symmetry. So it's not group-like at all. Okay. Now, we would like to generalize the Ising model that I introduced at the beginning to have symmetries given by arbitrary fusion categories, not necessarily just groups. And I will say something about why we would want non-invertible things later. And also, we may not want the simplest Boltzmann weight of e to the power beta x, but we may want something arbitrary and something that depends on the location on the lattice. So we replace this e to the power beta and this thing with some symmetric function at each edge that can vary depending on the edge. So once we generalize this model, we want to answer the following questions. So can we couple these to a gauge theory, or can we gauge some of the global symmetry? And how to generalize Kramers-Wannier? Okay. So again, directly answering this question by writing down the Partition function and doing manipulation on the Partition function is nearly impossible because of how intricate it gets, but we have better tools. And one of them is called symmetry topological field theory, or SymTFT. Let me kind of describe the idea in a vague way. So we are interested in a two-dimensional model, but a SymTFT, the SymTFT corresponding to this two-dimensional model is going to be a three-dimensional topological field theory that we are going to put on a space that kind of looks like this. So it has boundaries, these red and these blue boundaries, and inside the bulk we have this topological theory. So the topological theory means that the exact shape of this object doesn't matter. We can elongate it or we can shorten it. The Partition function is going to remain invariant. Now, if you cut this thing in the middle, then you're creating two surfaces. Now, at these two boundaries, we're going to have two boundary conditions. Say one of them is completely topological and the other one has, okay, whatever it is, maybe it's not completely topological. But whatever the boundary conditions are, corresponding to those boundary conditions, you are going to produce states at these boundaries by doing the path integration over these spaces, right? Let's call this red state topological and this blue state dynamical or something. Now, what this picture represents is the inner product between these two states, which corresponds to gluing these two halves of this block. And since this is topological, you can shrink this to a two-dimensional surface. So this is indistinguishable from this because the bulk theory is topological, and this is just a two-dimensional theory. So the point is that this three-dimensional topological theory with boundary is really equivalent to a two-dimensional non-topological theory if you have a non-topological boundary condition. And the reason that I'm introducing this is that this two-dimensional theory, we want this to be our Ising model. And we are going to realize this partition function by looking at this topological field theory instead of the Ising partition function directly. And as I was saying, that what we will do in practice is that we'll put a topological boundary condition on one side and a non-topological boundary condition on the other side. Okay, so the first question is, can we really write down the Ising partition function as an inner product of two states, right? Because that's the claim here, that if this is your Ising model, and if this partition function is equal to this partition function is equal to the inner product of these two states. So is the Ising partition function an inner product of two states in some Hilbert space? The answer is of course yes. So let me kind of sketch why. Consider the Hilbert space consisting of square integrable functions on your group. So these are just functions on your group that you can square and integrate and it will not diverge. If this is a finite group, it's not a concern at all. So this is a Hilbert space. There's some inner product. Doesn't matter really what that is. But this is the complete definition. You don't need to know anything else. Now define a Hilbert space for the lattice. So recall that the lattice was these kind of things where these were the vertices and these were the edges, right? So for each edge, take a copy of this Hilbert space and take a giant tensor product. So this is a very large Hilbert space. Now a generic product state in this Hilbert space is that you simply choose an arbitrary element from this L2G for each edge. That's this thing. And then choose another state that is not arbitrary. That's a very specific state. So here, suppose this is my lattice. So sigma is a field. This is my shorthand notation for summing over all field configuration. So sigma assigns a group element at each vertex. And so here you have a very specific combination. So for each edge, you have the difference between the group element here and the group element here, and so on. So then you sum, then you take a tensor product over all edges, and then you sum over all field configurations. Now I'm calling this a topological state. At this stage, it may not be obvious why this state is topological. So, and I'm not going to elaborate too much on it. Just notice that this is not arbitrary, and it does not depend on the choice of the Ising model. Whereas this will, because I will later say that these are going to be the Boltzmann weights. Now, what you can kind of immediately observe is that if you take an inner product between these two states, you really directly get the partition function of the Ising model that I previously wrote down, because this theta E is going to act on this group variable, and you are just summing over all field configurations. This is the definition of the Ising partition function. And the simplest example of the Z2 Ising corresponds to when you take your Boltzmann weights to be the exponential and G, the group, is just Z2 with two elements. This of course does not prove that you can write down the Ising partition function as a SymTFT in general, but and of course there isn't time to prove that, but I will give some sketches. Suppose we can realize a non-abelian Ising model using this SymTFT picture. So how do we answer the questions that I asked previously, that how do we couple this theory to a gauge symmetry? Well, so as I was saying, that this dynamical boundary condition, it will have all the information about the coupling constants or the Boltzmann weights of the theory. And this topological boundary condition, it doesn't know anything about the particular theory, but it knows about the symmetry. And the topological field theory in between also only knows about the symmetry. So this topological field theory and the topological boundary condition, this is universal given your choice of symmetry. The definition of the theory is entirely encoded in this non-topological boundary condition. And there are multiple choices for the topological boundary condition, and different choices will give you different gauged version of your Ising model. Without going into detail, let me just give some examples. So suppose, so this topological theory, because I should say that this topological theory depends on the choice of symmetry. More concretely, it depends on the choice of the symmetry category. And recall that vec G is essentially the same as the group G. So if you take vec G to be the category defining this topological field theory, then you have different choices of boundary conditions here, and one of the boundary conditions can itself be determined by this vec G. So basically, these boundary conditions are given by something called modules. The definition is not important, but I will give some examples. So one of the module is vec G itself, and that corresponds to gauging nothing. So it's just the standard Ising model with G global symmetry. And it's 30 minutes now. Sure. Okay. Another choice is vec. Again, I'm not going to give the definition, but I'm just going to say that this allows you to gauge the entire group. So now the interesting thing is that if you have a global symmetry G and you gauge the entire group, you may think that you don't have any global symmetry left, but if you work out the details, it will turn out that this this series has a global symmetry given by the representation category. And this is one of the reasons why I said that we need to consider non-invertible symmetries, because if you allow non-abelian group-like symmetries, then gauging will necessarily give you something that has a global symmetry that is non-invertible, given by representations. And we can also gauge subgroups if we want. Okay, now, what happens to the Kramers-Wannier type dualities? Well, this three-dimensional topological theory enjoys something called the mirror symmetry. This may be more familiar in the context of electric-magnetic duality in four-dimensional Yang-Mills theory, where we know that we can exchange electric charges and magnetic charges, and we get a dual description. This is kind of similar. So this topological field theory based on some category has a dual description in terms of another topological field theory in terms of a dual category. And you, of course, also have to change the boundary conditions properly. So if you take two dual theories and compute their partition function, recall that the partition functions correspond to partition functions of Ising models, you get the partition function of two dual Ising models. And our claim is that this is the proper generalization of Kramers-Wannier when you have non-abelian symmetry. Let me just give some examples. The simplest is, again, the Z2 Ising model, where the Boltzmann weights kind of look like exponents. This mirror symmetry changes the dynamical boundary condition given by the Boltzmann weights to another dynamical boundary condition given by the Fourier transform of the Boltzmann weights. And the Fourier transform of e to the power beta x is another exponential function up to some irrelevant proportionality constant. And here you can readily recognize the dual inverse temperature of Z2 Kramers-Wannier duality transformation. Now, if we start with an Ising model with G global symmetry that had some subgroup H gauged, then the dual Ising model would have a rep G global symmetry where the gauged part is rep G mod H and so on. For Z2 Ising, if there's nothing gauged, so this is the vanilla Ising, the dual Ising has a Z2 global symmetry. It's the Pontryagin dual, but that's isomorphic. But all of this Z2 is gauged. So here I would like to point out a subtlety. Usually people say that the Kramers-Wannier dual of the Z2 Ising is another Z2 Ising. It's not strictly speaking, if you take it literally, it's not true in the sense that it's Z2 Ising, but the Z2 is gauged. However, if you're on a simply connected manifold where there is no gauge moduli, the gauging Z2 does nothing, and then you truly have a duality between two Ising models. Okay, so far what I've said is very abstract, but how do we actually compute these partition functions? I don't have much to say, so I'll be brief. So this is just a graphical notation for tensors, right? So T mu is a vector. We can draw this vector as something like this. So you have a node where you have the name of the vector and you have one edge corresponding to one index. The direction of the edge gives you different locations of the index, covariant or contravariant. So if you have something like this where you have one edge between two nodes, that's simply a contraction of the two tensors. So if you have one node with three edges, that's a tensor with three indices and so on. So the point is, if you see a picture like this, you should think of this as describing a very large tensor. So for each vertex, you have a tensor, and each of these edges correspond to an index. And whenever there's an edge between two nodes, that gives a contraction of indices. So this is a massive contraction of a bunch of tensors, but ultimately this is a tensor that has 1, 2, 3, 4, 5 free indices. Now, these kind of things, where I claim that the partition function of this model gives you the Ising partition function, the way that we compute this is that there's a tensorial model for these things. So, this part corresponds to this part. So as you can see that here you have a very intricate lattice, and here you have some vertical edges. Similarly, on this red boundary, so here you have some intricate lattice with some vertical edges. And for each of these vertical edge, you have a free index of your tensor. Similarly here, and so when you glue the top and the bottom part, these two parts, you have a contraction of tensors, and at the end you get a number, and that number is your partition function. So all these topological field theory computations are they basically boil down to computing tensor contractions. Now, how do we get these tensors? So what tensors to put here, and how do they correspond to the categories? So the point is that the categories, while they have abstract definitions, they also have some very concrete definitions in terms of tensors. So when you're defining a category, you have to say what the objects of a category are. So for example, if this is a group, you have to say what are the elements of the group. you have to say what is the multiplication in a category. So if it's a group multiplication. If it's a category of representations, then it's the tensor product of representations. Then you have to say how to decompose the product of two things in terms of simpler things. And you have to say how many times a simple object appears in the decomposition of two other simple objects. So these are the multiplicity, and the multiplicities are given by vector spaces. Now, this part is a bit technical, so maybe I will skip some of the details. But the point is, the product in these categories does not have to be associated. So if you have three simple objects like this, and if you take the products in different orders, these things and this thing does not have to be exactly the same. They are necessarily isomorphic, but that isomorphism can be non-trivial. So the way that you specify the isomorphism is that you decompose them into simple objects. You look at the multiplicity spaces, which are vector spaces, and you have to specify the isomorphism between these two vector spaces. Now, if you define this data, that completely defines the category. Now, the objects of the category can be very abstract. They can be elements of groups, they can be representations, they can be completely different things that do not look like vector spaces at all. But the multiplicity spaces are always vector spaces. And the data you actually need to define the category are isomorphisms between these multiplicity spaces. So these are called F symbols, and they are always linear operators with many, many indices because these multiplicity spaces can be large. So the point is that these are simply tensors. So the way that you specify your category is that you give me some tensors. And using those tensors, you can define this kind of networks where you put those tensors at these points and you put your Boltzmann weights in some other nodes. And by contracting these two things, you get some numbers. So this is a very explicit computation. And the nicest part is that since this is just matrix multiplication, our modern GPUs are very good at doing this kind of matrix multiplications. So what have we said so far? Symmetry plays an important role in our understanding of phases of matter. And symmetries are not only described by groups, but by fusion categories. They can be non-invertible. They not only act on local operators, but they act on extended operators. And if we have a lattice QFT or an Euclidean QFT, we can compute its Partition functions by putting it on the boundary of one higher dimensional topological field theory. And dualities of bulk theories will imply dualities of boundary theories. Okay, and computations of all of these things can be done by computing contractions of tensors. So what are the open problems in these directions? I have only talked about two-dimensionalizing models, but of course we can try to generalize these for arbitrary dimensional Euclidean field theories using the notion of fully extended categories. And as I said, that our computers are very good at computing these tensor contractions. So we can very explicitly do Wilson RG on these models. So you take a lump of vertices, you replace them with some averaged vertex. And studying the effect of Wilson RG on these Partition functions and finding the Partition functions at the fixed points is a very active open area of research at the moment. With that, I will end my talk here. Thank you.
I have an announcement before we actually move into the question part, which I hope will be rather short. This is for the students. I think there is a session that is actually arranged for you to have a meeting with Dr. Munir Akbar Rana outside. So you'll first, after this session is over, you can go and meet him. And for the delegates, after the questions is over, we just simply move to the lunch and we again meet around 2:20. So we move to question answer session now. I mean, questions for Dr. Ishtiaq.
Yeah, you talked about the symmetries, Lie group symmetry. So the current is a local function, and can we think of some non-local symmetries, because on the Ising model the atoms are arranged on a lattice, so we can have a current which is defined at 2 points. So is there any possibility that we could quantum group symmetries?
Absolutely, yes. I mean, you will not have those symmetries in any arbitrary model, but if you pick your models correctly, especially if you pick an integrable models, I think you will always have non-local symmetries. So on lattices, they will look like operators that act simultaneously at different lattice sites that are separated by some finite distance. On continuum, they will look like multiple integrals over spacetime. So you will have some multi-local operators, an operator that depends on not just a choice of one point, but a choice of a bunch of points. And you have to integrate them for each point over your spacetime to get some kind of operator. So those are going to be the higher charges of your integrable systems.
Okay, thank you.
My question was on the tensor network. So can you move to the slide? No, the one above. Yeah, this one. So since if I'm not wrong, at every node there is a like operator, right?
Yes.
So
Well, there is a tensor, yes.
so since my operators are non-abelian, so what is
No. So these are not operators on a vector space. These are really just tensors with valid in real numbers. So yeah, like ordinary vectors or like the stress tensor or the metric or whatever.
Okay. So my question was like, does it tensor has any dependence, like if I calculate it from the left or to the right?
No.
Okay. Thank you.
Yeah, it doesn't matter in which order you take things.
Okay, so with this, I'm going to close the session. Ask him later. Actually, we're already running way behind. So as you remember, please rush to your lunch. This is for the delegates. And we meet back over here at 2:20 for the next session. Thank you.